Yeah, lack of attendance is clearly reflected in some of the exam scores. I mean, you could just grade an exam and totally see that someone is not attending. Some people have no idea what we are doing. Nothing. Because they don't show. But hey, I'm not the one getting a grade, huh? But to the rest of you, good morning. I hope you had a good weekend. And trust me, this week is gonna fly by so fast. And we're doing comparison tests, okay? Well, we're doing the basic comparison. And then today we'll do what's called limit comparison. But I have to do one more example. I got you. Balthazar, I got you, no worries. I hope you feel better. I asked you guys to go over factorials. Is your exam still on the 8th? Ahmed, such an irrelevant question. I don't know. I can't stop what I'm doing and look at the syllabus. But I asked you guys to go over factorials. I hope you did. But if not, we're just gonna define factorials. But yeah, most likely your exam is on the 8th. So this factorial thing, I'm going to go over it because it shows up a lot later on. And it says, let n be a natural number. Okay, a natural number is what we denote by n. N here stands for the natural set. This is a German letter right here. It's n. N is 1, 2, 3, and so on. That's what a natural number is. A natural number is a number that can be associated with your fingers. It's a counting number. Okay, then n factorial is defined as the product of n by n minus 1 by n minus 2 and so on until you get to 1. Okay, so you just take the natural number n and multiply it by 1 less than it every time. Okay, so for example here, 5 factorial is exclamation mark here means factorial. That's 5 times 4 times 3 times 2 times 1. Whatever that is. Okay. Also, well, we haven't defined factorial for 0. 0 also has a factorial. Oh, by the way, here I should say also 1 factorial is just 1. Okay, so just product of 1 by itself, 1. And 0 factorial, I was saying, is also 1. You might say 0 factorial is 0 times, I guess 0, but it's not. It's a 1, 0 factorial. And we'll prove why 0 factorial is 1. Here is a factorial identity that we're going to use a lot. Guys, we're going to be using factorials a lot. This is going to start showing up in the next section. So factorial identity says that n factorial is basically n, okay, then you have n minus 1, n minus 2, and so on. This itself is a factorial. Okay, that is n minus 1 factorial. That's how you can rewrite n factorial as n times the factorial of 1 less than n. All right, for example here, 5 factorial, which was 5 times 4 times 3 times 2 times 1, is the same thing as 5, and then 4, 3, 2, 1 is 4 factorial. 5 times 1 less than 5 factorial. Okay, and this is gonna help us prove why 0 factorial is 1. Okay, so again, here we know that yes, we're going to use the identity here. I guess Noah can see it, but here we know that n factorial is n times the factorial of 1 less than n. Okay, and you can plug in whatever you want as long as n is a natural number or a whole number that's non-negative. Plug 1 into this identity. Let n equal to 1. We're going to get 1 factorial equal to 1 times 1 minus 1 factorial. Okay, and obviously 1 minus 1 is 0. And on the left, we have just 1. So 1 is equal to 1 times 0 factorial. Okay, and this is what we are interested in, 0 factorial. This is the unknown. Unknown times 1, anything times 1 is itself. So you get 1 equal to 0 factorial. Okay, 1 times x, imagine this is x, 1 times x is just x, so x is equal to 1, where x is being 0 factorial. Okay?
Professor?
Yeah.
What's the proof that 1 factorial equals 1?
The proof that 1 factorial is 1?
Doesn't that assume that it's 1 factorial equals 1?
Yeah, you can use the same identity here. You could plug 2 in if you want. Plug 2, yeah, 2, you get 2, 2 minus 1 is 1. See, that's 1, so you get 1 factorial. And then
right, but then the same thing happens.
Yeah, so left hand is 2, right hand is 2 times 1 factorial, and then you just divide by that 2, so you get 1 factorial equal to 1.
Right, but you're still assuming it's equal to
that. Okay, so again, we are gonna revisit factorials and learn a little bit about the algebra of factorials and things that you can't do with factorials, guys. This is stuff that people do a lot on basically certain functions. For instance, n factorial is not, you can say, for example, you can say n plus m factorial is equal to n factorial plus m factorial. Again, this is something that people do a lot with certain functions, and we can't do that here. Okay, so just try to understand the nature of factorials, please. Okay, before the next section, the next couple of sections. But for now, we want to look at this special series. And here it begins with 0, not 1, and goes to infinity of 1 over n factorial. Okay, so if I were to expand this series a little bit, we get 1 over 0 factorial, and begins with 0, plus 1 over 1 factorial, plus 1 over 2 factorial, Again, very special series. This series is in a lot of those YouTube math videos because it's really interesting. And later we're gonna see why or what the value of the series is exactly. But for now, we want to know if this thing is going to converge or diverge. Okay, so again, if I write this a little bit, 1/1 is 1. That's 1 again. 1/2 factorial is just 2. 1/3 factorial is 6. The next one would be 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. Okay, again, we want to know if the series is convergent or divergent. That's all. And later, again, later on in section 11.8, I believe, we're going to find the value of the series. Okay, and here again, we're going to use basic comparison. Okay, because none of the other methods works. All right, if I let a sub n be 1/n factorial, well, you begin with the nth term test. Always begin with the nth term test. Do that in your head. Just do it in your head. You don't need to write this down. The limit as n goes to infinity of 1/n factorial is obviously 0. The denominator just gets big and bigger. So that limit is 0. Nth term test is not conclusive. Again, if the nth term went to anything but 0, then we would know that the series is divergent. That is not happening here. Next test would be what? Integral test? Yeah, good luck integrating 1/x factorial. If you call a function 1/x factorial, this is not a continuous function. It's not continuous. N factorial is continuous over natural numbers. It's not continuous over a real set or a real subset. I mean, I can't integrate a factorial from, like, let's say 1 to infinity. It just makes no sense because we can't plug in, let's say 1.5 into x or into n. Factorial 1.5, there is no such thing. Okay, so integral test, comparison test. Using basic comparison, remember that step 1 is for us to guess. Guess. Okay, what would you guys guess? Well, I gave you a hint. I actually already said that this thing is going to have a value. Later on, we're going to find that value, so it's convergent. But let's see why one would guess this is convergent. All right. If you look at the denominator of this of the nth term, the denominator is n factorial. The question is n factorial, or does n factorial grow fast enough for the whole thing to converge? You understand that? That's what we are asking. Does n factorial grow fast enough for the terms of the series to decline fast enough so that when you add them, you get a finite number? That's what we are asking. So you can always try to, in your head, compare the series to a convergent or a divergent, geometric or a p-series. A geometric series or a p-series, whichever. All right, and it turns out that this n factorial is bigger than any power function. Any power function. So it's gonna beat basically any convergent p-series. It will. Just think about it. Maybe I write the order of functions for you somewhere. Yeah, let me write that over here. This is the order of functions in terms of growth, in terms of how fast they increase. Okay, the least powerful function is ln, the natural, well, the log. A log function grows really, really slow, and we saw that. Okay, so this is always less than. Power functions are next. Okay, so if I have n to the power of p, n to the power of p is always greater than ln n. Well, not always, eventually. So ln n is less powerful than any power function. For instance, ln of n is less than n squared, or n cubed, or n to the 4. ln n grows much slower. And every power function is eventually less than any exponential function. So let's say r to the power of n, which has to do with geometric series. And then next function is the factorial function, n factorial. N factorial grows more rapidly than any exponential function, if you think about it. And we're going to see why in a second. And then the next is n to the power of n. This grows the fastest. It grows the fastest. Okay, so if yeah, that's it. All right, so if you think about it again, this n factorial again is more powerful than any, I guess, power function. And when you reciprocate that, then 1 over n factorial is going to decline faster than any convergent p-series. So we just guess convergent. Because the denominator, or I should say because 1 over n factorial declines fast. That's what we guess. Our guess might not work. Well, we're checking. We're gonna do the proof. It might work. It might not work. But that's the reasoning. Okay. And again, the unfortunate thing about the basic comparison is the guessing part that we don't like. The second part is you finding the proper sequence. So here we're going to find a sequence b sub n such that a sub n, which is 1 over n factorial, is less than this b sub n. Well, again, that's what the basic comparison says. Basic comparison says that if we have a sequence b sub n larger than our sequence a sub n, and the sum of b sub n is convergent, then the series of a sub n is also convergent. Okay, so again, when you guess convergent, then you have to come up with a sequence such that our sequence is smaller or equal to. Okay, so let's come up with the sequence. This is the harder part. And I want us to observe something. I want to come up. So again, we want to come up with a sequence whose terms are always larger than these terms. Okay. And here how it's done. 1 over 1 factorial. You can say that this is less or equal than 1 over 2 to the power of 0. Right? 1 is basically 1 factorial is 1, and 1 is equal to 2 to the 0 is 1. So this is a true inequality. Okay, also 1/2 factorial. 1/2 factorial is just equal to 1/2. This is less or equal than 1/2 to the power of 1. Well, that is a true statement because 2 factorial is also 2, and 2 is equal to 2. So this inequality is true. Okay, now 1/3 factorial. 1/3 factorial is basically 1/6. 1/3 factorial is less than 1/2 to the power of 2. Just think about it. This is 6. This is 4. 6 is larger than 4. So when you reciprocate, you get this inequality, which is also true. Okay, you could probably already see the pattern. 1/4 factorial. We can say this is less than 1/2 cubed. Now, again, if you think about it, 1/4 factorial, 4 factorial is 4 times 3 times 2 times 1, and 2 cubed is 2 times 2 times 2. So every factor here is greater than every factor, I guess. Therefore, when you reciprocate, you get less or equal. It's just less. It's not equal. It's just less. But that statement is true. Okay. So the observation here is that 1/n factorial is always less than 1/2 to what power? 2 to the power of
n.
Not quite. N minus 1. This is how you can, this is always true. N factorial is always larger than 2 to the n minus 1, always. You can use that. So 1 over that is the same thing can be said about the reciprocal. Okay? Yeah. And all right, so we just found the bounds. Next step. You have to see what happens to the summation of b sub n. So this is our b sub n. B sub n is 1/2 to the n minus 1. And by the way, guys, this series began being true starting at 1. Okay, 1/1 factorial. So yeah. But I mean, it's okay. So I'm just gonna drop the index. Just look at the series. What about the series? Convergent or divergent?
Convergent.
And why is that?
Because it's going to 0 fast enough.
No, that's not why. What kind of series is this?
Geometric,
It's geometric. And why is it convergent?
since the r is less than 1, it's
Yeah.
1/2.
Because r is equal to 1/2. So our absolute value of r is less than 1. That's why it's a convergent geometric series. Therefore, our original series is convergent. Converges by basic comparison test. There are so many series that you can compare this series with. Okay, I compared it to the series. Someone else can say b sub n is equal to 1/n squared. That works out too. 1/n squared is Is that right? Yes. Yeah, I mean, there are so many series that you can, or sequences that you can compare 1/n factorial with. Okay, I just used 1/2 to the n minus 1. Now let's look at something cool. So I am going to rewrite the series 1/n factorial. Again, in expanded form, it was 1/0 factorial plus 1/1 factorial plus 1/2 factorial plus 1/3 factorial, and so on. Okay. And we can say that this is less than, not less or equal than, it's just less than. 1/0 factorial is just 1. Okay. And we saw that 1/1 factorial, let me write that in blue here, 1/1 factorial in the previous page was less or equal than 1/2 to the power 0. Okay, and 1/2 factorial, this guy from the previous page right there, 1/2 factorial is less than 1/2 to the power of 1. Then we have plus 1/3 factorial from the previous page is less than 1/2 to the power of 2. And the next one would be 1/2 to the 3 and so on. Okay, so here we get 1 plus. Now, that series that we have in colors, right? This series here again is a geometric series. So I'm going to write that in summation form as the sum n going from 1 to infinity of, again, 1/2 to the power of n minus 1. Okay, so we're talking about this series. All right. And again, this is a convergent, it's a geometric series and it's convergent. So we can actually find the value of that series using the sum of an infinite geometric series. Here, the common ratio is 1/2. And the first term is 1. All right, just imagine there's a 1 right there. So the sum is going to be 1/1 minus the common ratio, which is 1/2. All right, so if you evaluate this whole thing, you're going to get what? We're going to get 3. This is going to be 2. 1 plus that is equal to 3. Okay, so this says something really powerful. It says that our series, the series in question, is less than 3. Just think about it. First of all, it means that this is convergent. And second, it's giving you an upper bound. An upper bound. This is telling us, this inequality tells us that the series does not go beyond 3. It's always going to be less than 3. Okay. And what number, guys, what number do you know of an important number do you know of that's less than 3?
E.
E.
Yes, E. Very important. So again, the most important number is pi, and I think E is as important as pi. It really is. Pi has been mentioned more often, but E is as important, if not maybe almost as important. But yeah, E is about 2.71, and 2.71 is less than 3. This inequality makes sense. But again, we're going to learn that this series it converges to E, a natural number, 2.71. Okay. Yeah, so this was a cool problem. It's going to be in the homework. This problem is in the homework. And if you look at the solutions manual, they do it differently. They compare it to a different series. You can compare this series to whatever convergent series you want. Compare it to 1 over n squared. It's going to work. Compare it to 1 over n cubed. It is going to work. As long as you pick a I guess, sequence that, I mean, look at that. N factorial is more than r to the n. It's also more than n to the p. So pick a p series that's convergent. Okay. Yeah. So the bad thing about the basic comparison, again, is the guessing part. We can get away with the guessing part. We can always try to do a comparison quickly in our head. And then the second thing is coming up with b sub n. Often that is not easy. Okay, so what we're going to do is come up with a different test, which is almost like the basic comparison. It's called the limit comparison. And the logic with the limit comparison is to pick a sequence that behaves like our sequence. It doesn't have to be less than or more than. It should just behave like our sequence in a long run. And for example, you have the summation of 1 over n squared minus 10, for example, or plus 10. It doesn't matter. Okay. So again, in a long run, when n grows, that minus 10 doesn't do anything. So again, imagine you plug in n equal to 1,000. You square 1,000, you get 1,000,000. 1,000,000 minus 10, that's not a significant difference. You have $1 million, take away 10 from you, you're not gonna go poor. Example, right? So 1 over n squared behaves like 1 over n squared minus 10 in a long run. And we know that this is a p sequence. We know that the summation of 1 over n squared is convergent. So this has to also converge. Very simple reasoning. I didn't have to come up with less than or more than. I don't have to worry about that. I just have to worry about picking a sequence or picking a function that behaves like our function. And that is the limit comparison test. Now, the way I do I covered limit comparison is different than the book. Okay, we'll do it in a way that it's always going to work. Okay, so my method always works. It requires less thinking than what the book does, and I want you to do it our way. Okay, but before me going over the comparison, the limit comparison, let's go over a definition, which says that if you have two sequence functions, again, each sequence is a function. We say that these two sequences are asymptotically the same if you took math 2 with me, you should remember this definition, asymptotically the same. If they behave the same way in a long run, or if they have the same end behavior. It's like a horizontal asymptote. Horizontal asymptote of a function describes the end behavior of that function. So if you have a function, f of x, your function is asymptotically the same as that horizontal asymptote, because in a long run, it gets to it. It has the same end behavior as that horizontal asymptote. Okay, so this means if you look at the ratio of a sub n to b sub n, we want a sub n and b sub n to become the same. Same meaning 1. If you divide two things that are the same, you get 1. But we want this to happen in a long run, meaning when n goes to infinity. Okay, again, think about this. If the ratio of two things is 1, then those two things are the same in a long run. That's what asymptotically the same means. When the limit of the ratio is equal to 1. All right, now I'm going to use a notation for asymptotically the same. We're not going to use equal sign. The equal sign is used when two things are always equal. Okay, but when two things become equal in a long run, we're going to use this notation. A sub n is asymptotically the same as b sub n. Okay, so that thing means a sub n is asymptotically the same as b sub n. Okay, just a short way of writing that limit. Does anyone not understand what this is? Did you guys get it? A sub n to b sub n becoming 1 or equal in a long run. All right, now, question is, how do we find a sequence that is asymptotically the same as another sequence? It's very easy. This is the easiest thing you guys can ever learn, okay? All you have to do is look at dominant terms. You have to see what dominates. So the question here is to find a sequence that is asymptotically the same as a sub n equal to, let's say, 3n plus 1 divided by, let's say, 6 n squared plus 10n minus 100. All right, so we want to come up with a sequence that behaves the same way as this sequence when n gets big. All you have to do, guys, this is very easy. All you have to do is take the dominant term on top and the dominant term in the bottom. That's it. Okay, so see what dominates on the top. The term with the highest degree or the highest exponent on top will dominate. That would be 3n. In the denominator, 6n squared dominates as n grows. So we say that this is asymptotically the same as the ratio of 3n to 6n squared. Reduce that, you get 1 over 2n, and that is your sequence b sub n. Okay, so 1 over 2n, and you can graph. Guys, try to graph this function, and graph this function. Zoom out. When you zoom out, you're gonna see that the two sequences will eventually overlap. They become the same. They graphically become the same. They converge onto each other when you zoom out, when n grows. Okay, you can also check by showing limit as n goes to infinity of a sub n to b sub n being equal to 1. Okay, because that's what the definition of asymptotically the same is. You can check that. Here, we'll just check this quickly. Limit as n goes to infinity of a sub n to b sub n. That's the limit as n goes to infinity. A sub n, let me just copy that down. It's 3n plus 1 over 6n squared plus 10n minus 100. Okay, we're going to divide that sequence by 1 over 2n. Basically, it's the same as multiplying by the reciprocal. Division by b sub n is multiplication by the reciprocal of b sub n, which would be 2n over 1. Going back to kindergarten, division by reciprocal division is the same as multiplication by reciprocal. Okay, so when you multiply 2n by 3n plus 1, you get 6n plus 2n, 6n squared plus 2n, and in the bottom, we have 6n squared plus 10n minus 100. And the limit of this function is just 1. You can use L'Hopital rule, sorry. You can use the L'Hopital rule to show that this limit is 1, but you can obviously observe that the ratio of the leading terms is 1. So this limit is equal to 1. Again, use L'Hopital rule, it proves it. Just take the derivatives long enough to get 1. Okay. Next problem, this is also important. we're going to show that, or here, let a sub n be sine of 1 over n. This is a very important sequence, guys. Sine of 1 over n, very important. And we want to find a sequence that is asymptotically the same as the sequence. That sequence happens to be the harmonic sequence. So let b sub n be 1 over n. We're gonna show that a sub n sine of 1 over n is asymptotically the same as b sub n, or 1 over n. In a long run, sine of 1 over n is going to behave like 1 over n. Don't believe it? Well, let's graph it. I'll just go to GeoGebra right here. Let me delete that. Let's plug in sine of 1 over n, or 1 over x. Sine 1 over x. Okay, this is the graph of sine of 1 over x. It behaves weird when x is near 0 because the function becomes discontinuous. We don't care about 0 here. We care about what happens when n grows. So let's also plug 1 over x. Guys, look at the two graphs. What's happening when n gets big, or when x gets big? What do you see? They look the same. They don't look the same when x is near 1 or near 0. Very different. But when n gets big, you can't even differentiate between the two graphs. They almost converge onto each other. They become the same. Okay? It's really cool. As a matter of fact, the graph of sine of 1 over x seems to be lower than, it seems to be smaller than the 1 over x. But when x gets big, the two become almost the same. Sine of 1 over n behaves asymptotically the same as, I should say, asymptotically the same as 1 over x. And we're gonna prove it. I think you have seen this proof before, but what you need to do is show that, so to answer the question, you just need to show limit as n goes to infinity of a sub n to b sub n is equal to 1. Let's do that. Let me go on to the next page. Okay, so here a sub n is sine of 1 over n. B sub n is 1 over n. Did I tell you guys someone or a couple of people on the first exam, they canceled the 1 over n's? Can't do that. We need to do L'Hopital rule, guys, because when n gets large, 1 over n goes to 0. Okay. 1 over n on the top, which is inside sine, goes to 0, and you get sine of 0, sine of 0, 0. So that's indeterminate. Okay. We could use L'Hopital rule. All right, take the derivative with respect to n of the top. The derivative of the top is cosine. Derivative of sine cosine of 1 over n times that by the derivative of, I'm just going to write it out, the derivative of 1 over n And bottom, we're going to be taking the derivative of 1 over n. Again, this should be a flashback. I've done this problem before. The derivative of 1 over n is common on top and bottom. That cancels out, and you end up with the limit of cosine of 1 over n. Cosine is a continuous function. You could just move the limit inside of cosine, do the limit of 1 over n, which is 0. We get cosine of 0, and that's equal to 1. That's exactly what we wanted to show. The limit of the ratio is 1, which implies that sine of 1 over n is asymptotically the same as 1 over n. Okay, I think it's my second time. So yeah, this was on the test, on the first test. This is, guys, this is a consequence of the limit as theta goes to 0 of sine of theta over theta. We are essentially proving this. This is being equal to 1. You have seen this limit in Math 7. We also saw it in section 6.8 when I began L'Hopital rule. This limit is 1. For theta small, sine of theta is almost the same as theta. Sine of the angle is almost the same as the angle. Okay, well, what does this have to do with sine of 1 over n divided by 1 over n? Just imagine if I let theta equal to 1 over n, just substitute theta equal to 1 over n in here. Okay, as n goes to infinity, n going to infinity is the same as theta going to 0. So sine of 1 over n divided by 1 over n becomes sine of theta divided by theta as theta goes to 0. These two limits are equal. Sine of 1 over n, sine theta over theta. They're the same. They say the same things. Okay? So what about the limit comparison test? Let's talk about that. Going back to series. This is still section, what is it? 11.4. So again, guys, remember the logic. We want to come up with a sequence that behaves as that is asymptotically the same as our sequence. Whatever happens to the series of that sequence is going to tell you what happens to the series of our sequence. Okay, so here is the statement. Let's say we have two series of a sub n and the series of b sub n. And guys, again, these have to be positive term series, or they could be eventually positive term. Okay, and yep. And the statement says that, number one, it says that if the limit as n goes to infinity of a sub n to b sub n is equal to 1. Okay, there are three cases for the limit comparison. First one says that if the two sequences asymptotically behave the same, they behave asymptotically the same, then the two series is going to behave the same. If the sequences behave the same, then the series behave the same. Okay, which means that the series A sub n and the series of B sub n both converge or both diverge. Again, think about it. If the two sequences behave the same way, then their sum behaves the same way. This is very intuitive. Okay, so that is the first statement. Second statement of limit comparison says that if the limit as n goes to infinity of a sub n to b sub n, imagine this limit is not 1, but 0 instead. Okay, and I'm going to ask you guys a question very soon, so make sure you're paying attention. Imagine the limit is 0 and the series of b sub n converges. So let's hold on and think about this a little bit. Imagine the limit is 0. Okay, well, a limit is 0 if the denominator is more powerful than the numerator. B sub n gets large faster than a sub n. Just think about it. Here, I'm gonna write that down over here. So this limit means that a sub n is much smaller than b sub n. That's what this says. The denominator is much bigger than the numerator. Okay, and imagine that the summation of b sub n is converging. So this is equal to some number m. It's convergent. Then, guys, can you tell what happens to the summation of b sub n? Should it converge or should it diverge? It should converge. This is basic comparison. Okay, so if a sub n is less than b sub n, then the summation of a sub n is also less than the summation of b sub n. And we just said that the summation of b sub n is finite. It's finite. So anything less than finite is got to be finite. Okay, that's a conclusion. If the series of b sub n converges, then the series of b sub n or a sub n should also converge. Okay, so I wrote down the reason down here. This is just a basic comparison written differently. Limit comparison is basic comparison done in a different format, pretty much. Okay, so if you got a zero limit and the series of B sub n converges, then A sub n is converging. If this diverges, we don't have a conclusion. All right, and we're gonna see examples very soon, maybe tomorrow actually. And then there's a third statement, which is exactly the opposite of the second statement. All right, imagine the limit of A sub n to B sub n is the opposite of 0 is infinity, I guess. Imagine this limit is infinity. And the series of B sub n diverges. Okay, so let's rewrite this, guys. If an to bn goes to infinity, then A sub n grows much faster than B sub n. Okay, this is telling us that A sub n is greater than B sub n. Just think about that. And we are also told that the series of B sub n is infinity. It's divergent. Okay, let's look at the conclusion then. By that inequality, the summation of A sub n is going to be greater than the summation of B sub n, which was infinity. Anything bigger than infinity is got to be infinity. That is a conclusion. If the summation of B sub n diverges, then the summation or series of A sub n must diverge. And we just did the reason. Okay. The book doesn't do the doesn't give you those statements, guys. They don't. They just give you a single statement, and they don't cover these two cases, unfortunately. And in the homework, there are questions where you got a zero limit or infinite limit. Students don't know what to do with those. So I kind of wrote the statement for those problems. Okay, but yeah, let's just end it right here. We'll come back tomorrow. I'm gonna do plenty of examples. Okay. Yeah, of the limit. The limit comparison is the easiest of all tests. The easiest. Okay, it requires zero thinking. It's really the opposite of the basic comparison, where you have to do guessing and coming up with the proper inequality or the sequence that satisfies a certain inequality. We don't have to do any of that. So your wish is always to get a question that where you could use limit comparison. It's just so easy. But yeah, we'll do examples tomorrow. Okay, so I'll see you then.
Thank you, Professor.
Welcome.
Thank you, Professor.
Thank you, Professor.
Thank you.
Professor.
Yeah, guys, think about these lessons, okay? Think about them. If you're not doing your homework, it's fine for today. But think about them. Think about these questions. I'll see you tomorrow. You're welcome.